Of the many types of equations you'll need to be able to write by the end of this module, the dissociation equation is both the easiest and the most deceptively difficult. In theory, it's the easiest. You have a whole thing. That whole thing falls apart to its pieces. Write an equation that makes that sentence true. But there are nuances to that equation. The atoms have to balance, which you already knew. But now the charges also have to balance because we're dealing with ions in solution. And not all of the subscripts can be subscripts anymore. And not everything dissociates because polyatomic ions have to stay together. So this video will point out some of the things to look for when writing balanced dissociation equations. Let me start by saying that we can write a dissociation equation like these for any salt, even those that are considered insoluble for this course. Now don't panic, you figure out what is insoluble in a later subsection. That's because a balanced equation should include what is likely to happen and a sprinkle of what could happen. If conditions changed, maybe the concentration of an insoluble salt is really low, or I increase the temperature of the solvent so that more can dissolve, or I force a dissolution with pH or other ions, then there could be aqueous ions on the product side. And as we will see in Gen Chem 2, all salts dissociate at least a little bit, though lots of times that little bit is teeny, nearly imperceptible amount. So if you see something that says only write dissociation equations for soluble salts, you have to ignore that. And honestly, you should probably ignore the rest of the materials that whoever that person is created. Those 4 reactions popped up at the end of the last section's lecture video. So I'll use these 4 reactions to explain how dissociation equations should be written. All 4 of these salts are soluble as written, at least initially. There's one with an extra subreaction later that you're not responsible for. Now I'm going to do these first 2 salt dissociations in parallel because I'll have the same things to say about both of them. That's because KBr and barium sulfide are 1-to-1 salts. There's one cation for every one anion. Because they're 1-to-1 salts, we will not need to worry about coefficients on the product side as everything will need to be in a 1-to-1 mole ratio. We will need to remember though that once the solid salt is placed in water, hydrated ions will form. These ions will have charges associated with them. All 4 of the ions formed are monatomic, so all 4 of the ions formed are going to have common charges dictated by their placement on the periodic table, as seen in the nomenclature module. Potassium is a group 1 cation. Cation potassium will carry a 1+ charge because group 1 elements will lose a single electron when they form their ions. Bromine is a group 7 element. When bromine forms an ion, it does so by gaining 1 electron to form the 1- bromide ion. All of that 1+ and 1- language has to make its way to our balanced equation. So when KBr dissociates in water, I have to say that potassium and bromide ions are formed. Simply including K and Br without the charges is incorrect because just the elemental symbol represents an atom and not an ion. It's kind of double incorrect in the case of bromide because bromine is a diatomic element. These ions are in solution now, so that needs to be included in our equation as well. Sometimes the chemist will include the solvent above the reaction arrow, kind of like this. You'll see this a lot more in organic reactions than with the reactions present in Gen Chem. I'm just showing you so that you know what it is. This is not something that you have to reproduce for me. At this point, you would want to double check that this equation is both atom and charged balanced. Because the dissociation equations start with a neutral salt, KBr in this case, both sides of your equation should add to 0. 1 positive and 1 negative charge fits that bill. The barium sulfide salt will follow a similar pattern. There's 1 cation, 1 anion for every mole of the salt. So when the salt dissociates, the coefficients of all the reactants and the products should be 1. The difference this time is that the barium is found in the second column of the table. Alkali earth metals lose 2 electrons to form 2+ cations. Sulfur is in group 6, the main group, and this group will gain 2 electrons when they form anions. So the sulfide ion will have a charge of 2-. Again, the ions on the product side are now in the center of sphere of water molecules, so they're aqueous ions, and aqueous or AQ has to be included after them. Note that even though the magnitude of the charge is higher on these ions, the sum of the charges on the product side still adds to 0. As you learned in the nomenclature module, not all of our salts have cations and anions that are present in a 1-to-1 ratio. We're going to have to take extra care with these salts, as our reaction will still need to be atom and charge balanced, and whatever that reaction is has to describe what's actually happening chemically. Now, to elaborate on this last point, let's look at the Lewis structure for CaCl2. I know we haven't covered Lewis structures yet, so I need you to not panic if the image looks foreign. We're going to do this much better in Module 6. But super briefly, the chemical symbols here represent the elements present in the compound, and each dot is going to represent a valence electron. The dots between the atoms are those that are transferred between the cation and the anions. The ones that are only around the anions, in fact, belong only to the chlorides. Now, this image is here to help you visualize what's meant by this 2 in the chemical formula. It does not represent a molecule of chlorine, which is a pretty common misconception. Chlorine is in fact a diatomic element, but it's not a diatomic ion. Notice that there is one single chloride on each side of my calcium ion because chlorine forms monatomic ions. When calcium chloride dissociates, it's going to form 3 separate hydrated ions. Now, why did I go through all of that? To illustrate why I can't bring the 2 that's a subscript in calcium chloride over to the product side as a subscript, which is shown here. This particular chemical formula on the product side is for a molecule of chlorine that has somehow gained an electron. Now, this malarkey looks very different than the 3 separate ions that actually form. So instead, to tell the picture of the 3 separate ions, you have to move that 2 out of the subscript spot and you'll make it a coefficient for the chloride ion instead. Now, these products that are included here actually describe the chemical process that my salt underwent. This subscript coefficient thing is going to happen with all of our ions, not just those formed from the diatomic elements. All right, one last big point that's going to make our life easier actually, and that is that polyatomic ions will not dissociate any further. They're present in your salt as a group of atoms, and that group of atoms is carrying a charge, so they will remain a group of atoms that carry a charge even after salt dissociation. Do not break these down into substituent elements. Once you remember to keep the band together, dissociation equations for salts that contain polyatomic ions are going to work just like all of the other dissociation equations that you can write. Determine the charges on the cation and the anion. In this case, you know the charge on the sulfate, which is 2 minus, and you can use that to determine the charge on the iron cations. Lastly, remember to move the subscripts in the salt from the reactant side to the coefficient positions on the product side, and to indicate that you now have ions in solution by including AQ as the state of matter on that product side. Lastly, double check that your atom count and the sum of the charges on both sides of the arrow are right so that you confirm that you're correct.